Hello, everyone. My name is Abhinav Bhatele, and I am a professor of computer science at the University of Maryland. And I am one of the co-organizers of this SC21 tutorial on user-centric automated performance analysis of hybrid parallel programs. This tutorial is on November 15th, 2021, and it runs from 9 a.m. to 5 p.m. All of the materials for this tutorial are available on the website mentioned here on the slides, hpctools.tutorial.github.io. I'm going to turn off my video so that it does not block a portion of the slides. In this first session, we will provide a basics of performance analysis and talk about the performance tools that we will cover in this tutorial. And this information will be useful in the subsequent sessions of this full day tutorial. So do you feel frustrated because your parallel program does not perform well? Do you feel like smashing your keyboard or the remote parallel cluster you log into? If the answer to those questions is yes, you have come to the right tutorial. In this tutorial, attendees will learn about some performance analysis tools that are commonly used in high performance computing, specifically Caliper, Timmery, HPC Toolkit, and Hatchet. Attendees will learn how to annotate their parallel programs for performance analysis, and then they will learn about different tools they can use and their basic usage. With that knowledge in hand, attendees will learn how to analyze performance using different tools and understand why their code might be running slow. Before we talk about the basics of performance analysis, let me introduce all the organizers. David Boma, Stephanie Brink, and Olga Pierce are from Lawrence Livermore National Lab. Jonathan Madsen is from AMD, and John Miller-Crummy is from Rice University. Together, all of us will cover different aspects of this tutorial. So let's get started. Oftentimes, the parallel performance of a program might not be what the programmer or developer expects. So the question is, how do we find performance bottlenecks in our program? Performance analysis is the process of studying the performance of sequential or parallel code and identifying why performance might be bad. Now, performance analysis is challenging even for sequential programs, and it's even more complex for parallel programs running on high-performance computing platforms. There are a variety of performance concerns, such as the computational performance of the CPU and accelerators connected to them, data movement costs within and between memory spaces of these different components, data movement of the network, which can be due to inter-node communication and I/O, and file system access. In addition, the complexity of hardware and applications has been growing as we move toward exascale. There are multiple compute engines on our parallel hardware with different complex memory hierarchies. There is often a large gap between programming models and their implementation. And increasingly, many runtimes and programming models are asynchronous, task-based, which also makes performance analysis more challenging. In addition, there are many different ways in which we can hurt performance when writing a parallel program, and I'll list a few of them here. There might be sequential performance issues in a program. A few examples are inefficient memory access when there is data movement in the memory hierarchy, or inefficient floating point operations. When you write a parallel code, there might be load imbalance when some processes or threads do more either computational or communication work than other processes. Communication issues or parallel overhead can often be a problem that can lead to performance issues. Many times, codes will spend an increasing proportion of time on communication as they scale up, which we often refer to as parallel overhead. Then there might be insufficient parallelism in our program to be able to scale to a large number of processes, which can again hurt performance. Next, sometimes there is more computation when you run in parallel as opposed to sequential code. This is sometimes referred to as algorithmic overhead or replicated work, which can also hurt performance. In other situations, people might perform extra computation speculatively, but then not use it all in the end, which is referred to as speculative loss. When running a parallel program, there might be complex dependencies between computations spread across processes or threads, And when there are long chains of these dependencies, they can slow down a program. People often refer to these as critical paths. Finally, there might be bottlenecks, which can slow down the program execution. Serial bottlenecks is one example where one process is doing some computation and it holds everyone up. Now, when you are doing performance analysis on a parallel program, either one or many of these problems might be happening together, and it's really challenging to do performance analysis. So let's see how performance tools in high performance computing can help us overcome some of these challenges and help us identify why our performance might be bad and help us improve our codes. So the simplest tool that people have used for performance analysis for the longest time is putting timers in your code. So let's say you have 3 phases in your program, phase 1, phase 2, and phase 3. You can put timers around them and print out the time spent in different portions of the program. This can help users identify what code regions or phases in my program do I spend most of my time in, and then focus their efforts on those times. However, this only tells us that specific regions are slow. It does not tell us why those regions might be slow. This is where more sophisticated performance tools come in. There are 2 broad categories of performance tools: tracing tools, which record time series data during program execution, and profiling tools, which collect and provide aggregated information. Profiling tools often use statistical sampling or instrumentation, and we'll talk about that in a few slides. Finally, there are some tools that also support both tracing and sampling, and you could use either depending on the use cases of your performance analysis. Tools will often record a variety of metrics, for example, counts and times of function invocations, time spent in different regions or functions in the code, number of messages and bytes sent, if we are looking at communication performance, and different hardware counters, whether they're on node or network counters, etc. Now, when we try to understand performance, we want we want the tools to correlate such metrics to the source code. And we'll talk about how some tools can help us do that. Now let's see a little more detail about tracing and profiling tools. Tracing tools record a time series of events in the program with timestamps. Some common events that are often recorded are function calls, MPI events, call path samples, GPU operations, etc. And if you were to visualize a trace that's collected by a tracing tool, it might look something like this. This is a visualization from a popular tool called Vampire. And the image here shows the different events that happen on different processes and communication through black lines. You can also aggregate information from a trace to look at aggregated data, such as in this figure on the left, which shows the communication matrix of the volume of data exchange between different processes. These are some examples of tracing tools. I won't read all of them, but the 3 that we'll cover in this tutorial are HPC Toolkit, Temery, and Caliper. As opposed to tracing tools, profiling tools ignore the specific times or timestamps at which events occur. They provide aggregated information about different parts of the code. Some popular examples of profiling tools are gprof and LinuxPerf. MPIP is a profiling tool for collecting MPI information. And then again, in this tutorial, we'll cover HPC Toolkit, Caliper, and Temery, which provide profiling capabilities. If you work with Python codes, cprofile, PyInstrument, and Scalene are some popular profiling tools for Python programs. So in this tutorial, we'll focus on 3 measurement tools, which are Caliper, HPC Toolkit, and Temery. And we'll also look at one analysis tool that helps us analyze the data that comes out of these tools, which we call Hatchet. HPC Toolkit also has a graphical user interface called HPC Viewer, and we will also talk about that in this tutorial. So let's talk about different ways in which profiling tools collect information. There are 2 main ways. One is called statistical sampling. In this case, we probe the program counter at regular intervals at some regular frequency. And when a sample is recorded, we attempt to unwind the call stack to derive the calling context. This lets us figure out who calls a function when a sample is recorded in a particular function. Sampling is often low overhead and does not perturb program execution significantly. As opposed to sampling, instrumentation refers to adding code either in the source or the binary, which we refer to as additional profiling code when we execute the program. Now, instrumentation can result in significant overheads and slow down the execution. There are different methods for doing instrumentation. If a user were to manually insert code in their program, that is referred to as source instrumentation. Compiler instrumentation is where the compiler automatically adds some code while it compiles the executable, the program into an executable. Binary instrumentation refers to modifying the binary either statically or dynamically to add profiling code for the execution. And finally, runtime instrumentation refers to modifying the program at runtime and specific parts of the code. So I think the last part of this tutorial of this session is about the output of profiling tools that we cover in this program. There are various different levels of granularity at which we can collect and output information from profiling tools. Many profiling tools, such as gprof, will provide a flat profile, which is a listing of all the functions in your program with counts and execution times. Tools will often also provide a call graph, which is a graph of all the caller-callee relationships in the program. Some tools provide a more detailed call information, which we refer to as calling context tree, and I'll explain that in the next slide. So let's talk about a few terms that will be useful and will be used in various sessions in this tutorial. Calling context or call path refers to a sequence of function invocations leading to the current sample. So in the image on the right, if we record a sample in PSM2 and PSM2 is called from MPI, which is called by physics, and physics is called from main, that sequence of invocations is referred to as the call path or calling context for that particular sample. A calling context tree is a dynamic prefix tree of all call paths in an execution. So if we were to merge different call paths in a program, we would get a calling context tree. If we merge nodes in a calling context tree that have the same name and create a single node for those, that is referred to as a call graph. We still have caller-callee relationships, but in a call graph, we might not have metrics for the node depending on the context from which it was called. So let's look at a more detailed example on the next slide. So here the image on the left is a calling context tree. You can see some functions such as grold and garply are called from multiple functions, and so each individual calling context is recorded. Each node in a calling context tree might have different kinds of information associated with it. So there might be contextual information such as the file and line number for this function, the function name, call path, etc. We might also have performance metrics on each node, such as execution time, floating point operations, and many other hardware counters. Oftentimes, these performance metrics are recorded per process or per thread. So you might have a thread ID and the specific metric recorded on that particular thread. Now, as I said earlier, if you combine all the nodes with the same name, you get a call graph from a calling context tree. The caller-callee relationships are preserved, but in this case, we might combine all the metrics across the different calling contexts for a particular function. So many different profiling tools output either a calling context tree or a call graph, and we can analyze them to understand the performance of our code. The last slide in this first session provides a high-level overview of the functionality provided by the different measurement tools we cover in this tutorial. So all of the tools, Caliper, HPC, and Toolkit, and Temery have support for C, C++, and Fortran programs. So you can profile any of them with any of these tools. Those are the popular languages used in high-performance computing. If you're working with Python programs, Temery also has support for profiling Python programs. In terms of how these tools collect information, Caliper and Temery support both sampling and instrumentation. HPC Toolkit provides sampling support for generating calling context trees. In terms of what information you can get when you use these tools, all of the tools support both profiling and tracing. These are different modes in these tools. So you have to use different settings and different options for enabling one or the other. So that brings me to the end of this first session. That was an introduction to the basics of performance analysis. Again, the website for our tutorial is listed here, hpctools-tutorial.github.io. All of the materials, the PDFs for the slides, and the exercises are available on this tutorial. And in the next session, we'll start looking at some more details of each of these performance tools. Thank you.